Welcome to this brief video where I'm going to be demonstrating the new floor plan extraction tool that we've recently put into n4ce, and it makes its debut in version 4.3. I'm going to start by putting a section through this data. So if I just do a quick align to Z, that'll give me a section throughout the entire data set. Obviously it's clipped to the extent of the data, so I'm not too fussed about that for the time being. All I'm really worried about is what the actual section sees. Obviously I can raise and lower the section like this, and what I want to do is I just want to zoom in, and I'm going to right click and drag in this bottom view, and as I do that I can alter the position of the section. And what I'm going to do is I'm just going to slide it to a point where I think I'm going to get a good section. So here we go. That looks nice and clean there. Alright, so that's the position of my slice through the building, my initial slice. I'm going to go to the feature extraction menu, come down to the floor plan helper. So the algorithm works by fundamentally breaking these sections up into smaller cell sizes and analysing each size individually. So here we've got the cell size currently set to 150 mil or 0.15 of a meter. So basically the entire data set is going to be split up into the cells of that size, and then the software is going to analyze the data in each cell independently on multiple threads to try and see what line work it can find. Here we have the number of points per cell that there must exist, otherwise it won't even consider, and also the minimum number of points on a line for it to be considered. These essentially just weed out the noise, so it stops the algorithm bothering to check data that isn't even worth checking. We have the minimum percentage of coverage essentially on the line, so when it finds a line in the data, it checks to make sure at least 35% or whatever the number may be of that line is covered, so that if you want to pull out the most realistic and accurate data, then you'd up it. If you want it to be a bit more carefree, then you would lower it. Once the algorithm's finished most of its checks and pulled out the line work, the last stage is to extend the line work to the edges of the cells if there is data there. And that's what the extended point cloud does. You can also tell it to check for curving. By default that's turned off. Hand in hand with that is the straight line tolerance you have here. So basically what that means is that if you join the ends together, then all the points must be within that perpendicular distance from the line to be considered straight. If they were outside, then that line would be considered curved or available to be curved, and then the algorithm would proceed according to plan from then on. So after the curve check, we've got the cell size, as I started off by saying. So that's one of the most important settings. That defines how smaller areas the data set is cut into. Obviously, you don't want to go too low, because if you go too low, then you're basically introducing yourself into the noise of the section itself. So you want something which is significantly longer than the noise of the section. The minimum line length to extract. So again, this helps to remove false positives. So if we're saying our cell size is 150 mil, then we basically want to say, well, don't pull out any lines shorter than 80 mil. Those lines will be clean lines, and they won't perhaps be at funny angles where it might have been able to get a line just about. The 2D range is used to detect data that is wholly horizontal or wholly vertical. So basically the dx and the dy is analysed, and if they are within this tolerance, then it basically goes a different route in the software. There's no point trying to do a best fit if the data is perfectly horizontal and perfectly vertical essentially. Then you have the coefficient here. So this is to check that basically all the data, when it's doing its best fitting, is going to be a good fit. So 1 would be the perfect fit, which would mean all the points lie perfectly on the line, which is obviously unlikely, and then you can lower it to suit. Reasonable values seem to be about sort of 0.7 onwards. If you lower it too much from there, you can introduce some erroneous lines. You can also, if you want to, introduce the standard deviation check. So essentially any points that are outside the standard deviation of each best fit will be discarded. So that can also help to remove noise. Not usually needed, but it's in there in case. This delta here is the length, or rather the thickness of the histogram cells that are used when identifying the line work. So it basically splits the data up into those cells, as I previously said, and then it essentially rotates around the origin and tries to find all the lines that line up with the various lines, a bit like a clock. But then it has to then compartmentalize that data into various thicknesses, and that is the thickness. And that should basically match the noise or be a little bit larger, because then it will hopefully get most of the noise in one go and you won't cut it up at all. When it has found lines and joins them together, it then tries to simplify them. That's what the Douglas-Quirker setting does there. Any points, so smaller values will preserve points, larger values will clean out more points. As I said, the straight line tolerance is used to tell the difference between a curved line and a straight line. If two lines are going to be joined, as in one in front of the other, they must lie within that tolerance of each other. So the second line can't be greater than that value, otherwise it won't be joined. When it does do an extend to another line, that line must be within this tolerance, otherwise it won't be joined. So that tries to stop lines being joined across doorways and windows, that kind of thing. If two lines are found either side of some scan data, like it could possibly be if the noise data was if the scan data was quite noisy, then you'd end up maybe with two parallel lines very close. So this tolerance says if the lines are within that tolerance, then basically merge them to make one. And this final tolerance here is the tolerance that's used to join line work that could be at an angle to another line. So for instance, 40 degrees, 45 degrees, 90 degrees or whatever, it won't join them if the ends aren't that close. So that tolerance will be used to join line work that meets the 90 degrees in the corner. Say if there wasn't enough data to go to the corner, then that tolerance should hopefully join the lines so that they meet in the corner. Usually you want to give it a code as well, so I'm just going to give it, say, BD for building, and just zoom out a bit and hit extract. Okay, and there we're done. So you can see the red line there is the line work it's extracted. It's not going to be perfect. There's going to be places where it needs to be joined up, places where we need to remove data, as you can see here. Let's have a look. But on the whole, that's done a reasonable job. If I zoom out, you can see there's still places that it needs to be tidied up. There's a few problems with the algorithm that we know about, which will need to be fixed in times to come. But fundamentally, we're okay. Some lines have been missed because they were chosen, or rather this line was chosen instead of that line, and sometimes the best way of getting around that is to reduce your cell size so that you can essentially separate these two lines from being in the same cell. So if I want to now commit that, I just come down and choose commit all. Just before I flick to the project, I'm going to save this data as an image, because then obviously I can use it to help me tidy up the line work afterwards. So under sections, I'm just going to come down here. Now I could use the button below to create custom images or custom sizes and tilings and all the rest of it, but I'm just going to go for a quick 8K. Floor plan. Okay, and now I can go into the modeler and start joining and breaking and extending the lines that I need to. Okay, so now I have the data in the standard 2D view. I've got the image backclothed. If I just turn the backcloth off quickly, there we go. So we're going to need to tidy up some of this, obviously. So I'm going to go to the lines menu. So I'll start just by using the delete tool. And we'll delete that line there, don't want that one. Delete that one there. Now I need to do some joining. So we'll go to join that to there, that to there, that to there. And we probably don't need that line at all there. So Alt-M delete, Alt-M join. Okay, so I need to fillet those corners. So under lines, I'm going to go down to segment, and we're going to go into merge fillet. I will average out the point heights, even though they're basically all the same. Move on length basically means take the corner points where there could be two, for instance, here and here, and replace them with one. So I do that there, do that there. Now here it's a bit different. We need to create the corner in there. So I'll carry on and go to the corner option and select the line that I want it to be perpendicular to, which would be this one, and then click that node there. You can delete those nodes as well. So let's go points, delete, in rectangle mode, get rid of those. RM join, delete. Okay, and you carry on. Okay, and obviously I can just keep turning the backcloth on and off to check my progress as I go. That concludes the video.